Okay. Okay. Morning, guys. So last time um, we laid down some foundation about what is information retrieval, right? So and specifically, we say that the the definition of information retrieval is that given some information need about some unstructured documents, right? You want to be able to retrieve a subset of the documents that satisfy your information need, right? So, and in particular, we talked about one very simple but basic model in information retrieval, which is the Boolean retrieval model, right? And we say that this retrieval model is basic, but it's very effective in the sense that you can accurately specify what you want, and the model returns you exactly a set of documents, right? So in the process of doing that, we say that one data structure was eminent and very useful, which is called inverted index, okay? And that inverted index comes in two parts, a dictionary and postings, okay? So today we're going to focus more on the details of these data structures, okay? In particular, we're gonna talk about how to implement the dictionary, all right, and how to do tolerant retrieval. Okay, so by tolerant retrieval, we mean that you want to retrieve documents which might not exactly match the query, but close to the query. Okay, so you want your retrieval to be tolerant to errors um, or noises, either intentionally or unintentional. All right, so this is sort of the roadmap of the lecture, okay? The first part of the lecture. So we will talk about dictionary data structures, then tolerant retrieval, in which I will talk about three cases. One is wildcard queries, where you see things like the stars in the middle of your query, okay? So I'm sure you guys know regular expression where you can specify a wildcard uh, in a string, right, to represent uh, sort of a number of variants, okay? And the second topic will be spelling correction, right? This is very common in search, where you could either type in something incorrectly, unintentionally, and then the system should be able to correct your typo, all right, and then retrieve the correct documents. Another possibility is that the documents themselves may contain typos, all right, and the query is actually correct. So how do you make that match, all right? And the third thing is called soundex. So I touched on this a little bit last time. Essentially, this is matching between query and documents based on the sound of the text. Okay, so here's what we learned last time. This picture shows you the essential logical structure of a inverted index. All right, so we have the dictionary and we have the postings. Okay, so how do you actually implement the dictionary? Right, I think I mentioned it briefly last time that the dictionary is actually just a collection of words or terms along with their frequencies. And at the same time, since every dictionary term is associated with a posting list, you need to maintain a pointer. Okay, so in actual fact, this dictionary is stored as a separate file from the postings. Okay, so you can imagine that the most naive approach to construct such a dictionary is to use an array of structs, right? Where every element of the array is a structure that contains three things: the term, the frequency of the term in document, in your document collection, and the pointer to the posting list. And remember, the posting list is just a number of document IDs, right? In which this term appears. So, but then if you look at it this way, right? A term itself, assuming that your term is no longer than 20 characters, Okay, let's talk about English for now. And that's going to take 20 bytes, right? One byte per character. And if you're talking about decimal frequency, which are integers, right? So depending on your architecture, it takes either 4 bytes or 8 bytes, right? Depending on whether it's a 32-bit architecture or 64-bit. And similarly here, the posting is also, it's an address, right? So it's also an integer, 4 to 8 bytes. So this means that every entry in this thing takes as much as 36 bytes, right, in total. So when you have a very large dictionary, this can take up quite a lot of your space, right? So that's one thing. So how do you store the dictionary efficiently? Okay. And number two, once you have stored such a dictionary, how do you search it? Okay. Because the general procedure of the retrieval is that given a query, let's assume that the query is a term, right? So you need to quickly search through your dictionary to find the entry and then get to the pointer, right? And then from the pointer, you can chase the posting lists, right? So how do you quickly look up the elements at query time, right? So we need to design data structures that can both store efficiently the dictionary and search the dictionary quickly. So generally speaking, there are two choices which are familiar to you, right? One is you can use the hash table. The other is you can use trees, okay? So some IR systems use the former, some use the latter, right? There are some pros and cons associated with these two choices. So for hash table, as you know, the advantage is that it's very quick in the lookup, right? It's order constant, okay? Order one, lookup um, faster than the tree. But the downside is that there's no easy way to look for minor variance, right? So imagine that if you have these two words, right, judgment and judgments, this is the American spelling, right? This is the British spelling. And even though that the two words are exactly the same, modulo this little small difference, which is the missing of E here, okay? If you hash it, these two words will completely be hashed to different buckets, right? So they will be two different words. That's number one. Number two, there's no easy way to do prefix search. Okay, by prefix search, I mean that, for example, I want to look for all terms starting with J and U. Okay, so there's no easy way to do this. Again, because once you hash it, there's no locality anymore. Okay, the words that appear close to each other by their lexicographical form are no longer close to each other in the hash table, right? So that's the downside. Another thing is that if your vocabulary keep growing, right? So you need to occasionally do rehashing, okay? You need to do rehashing because there's some imbalance, right, in the hashing. Over time, if the hash table becomes extremely imbalanced, the performance will degrade and it becomes linear, right, to work neatly. So you want to do rehashing. That is, you need to adjust your hash function. So this is very expensive. Okay, so the alternative to that will be to use trees, right? Obviously, trees is not as fast in terms of lookup as the hash, right? It's logarithmic time if you have a balanced tree. So this is an idea of, this is just a sort of schematic of how to represent a dictionary using a tree where each node is actually a prefix of your keys, sorry, of your terms. Okay, so you can see that the root one has two branches. One is all the words starting from A to M. The other is all the words starting from M to Z, right? And then you go down and split further and so on. Okay, and at the bottom of your tree stores all the actual terms in your dictionary. Okay, so the dictionary is actually here, but you can access the dictionary items through this tree. And this is a binary tree. Another option is to use a structure similar to the one in database, okay, which is called B tree. So the difference is that now the fan out, the degree of the tree is no longer 2, but is some variable. All right, so it varies from a certain range, right, from A to B, where A, B are appropriate natural numbers that can be calculated, right, depending on sort of the size of the subtrees. Okay, so I think you should have learned this in your database course. All right, so the obviously the pros of the tree is versus the hash table is that now it solves the prefix search problem, right? Because with the B tree or the binary tree, you can get to sort of, you maintain the locality of the terms, right? But the cons is that it's slower than the hash table because it takes logarithmic time. Log m, where m is the size of the tree, right? The total number of items in your dictionary, and provided that your tree is balanced, okay? If it's not balanced, then you have to rebalance the tree, which is quite expensive. But of course, B tree sort of mitigates that because B tree can sort of rebalance itself, all right? Um, so now, once you have these data structures, suppose that you have B tree or binary tree, okay, you can handle some kind of tolerant retrieval tasks. Okay, so let's get to the tolerant retrieval task now. So the first tolerant retrieval task is to answer wildcard queries. Okay, that is queries involving star. So suppose that you want to find all the documents containing any word beginning with MON. Okay, in other words, your query is MON star. Okay, so this is very easy with the binary or B trees. Okay, so all you have to do is just to search for any words within this range, right, from MON to MOO. Okay, anything in between is in that range, right? But on the other hand, right, if you want to search for any word that ends with certain character, like this, right, star MON, which is essentially a suffix search, that becomes more difficult with an ordered tree, an ordered index like B tree, right? But of course, you can build another B tree, which is reversed. Okay, you can index from backward, right? And then you will still be able to answer such query by just searching for this range, right? NOM to NON, where this is just, you read it backwards, right? NON, and there you go. You can find this. You can do this. Okay, this is a quiz. Consider this, right? Consider this wildcard query, PRO star SEN. How can we enumerate the terms meeting this query? Okay, you can write down like a couple of sentences. Okay, so let's carry on. Right, so at this point, right, we have learned a way of enumerating all the terms in the dictionary that satisfy certain wildcard query. Okay, but that's not enough. Once we have all these enumerated terms, we still have to get to the posting lists, right? So consider this query, right? If you have this SE star AEN FIOL star ER, right? So this query consists of two wildcard queries. Okay, so of course you can enumerate this and it becomes a number of words, right? and then you can enumerate this, and it becomes a number of words. And because guess what? When you want to do AND, you have to multiply them, right? So that will actually end up with a lot of executions of many Boolean AND queries, right? So it's like if this thing is A and B, this is C and D, then you need to do A, C, B, D, and so on and so forth, right? So that's a lot of Boolean queries that you have to execute, okay? So in order to sort of handle this, right? Another thing that you need to handle is that, so just now I showed you that if your star is in the beginning or the star is at the end, right? We have ways to do this, okay? But like what I just asked you in the quiz, right? What happens if the star is in the middle of your term, okay? So we could do this, right? We could look up CO star and star TION, okay, in a B tree and intersect the two term set, okay? So this is very expensive, right? So one solution to that is that we can transform the wildcard queries such that the star always appear at the end, okay? So the idea is that we can rotate this query in such a way that the star appears at the end. So once it appears at the end, we can use a normal B tree or binary tree to handle it, right? Okay, so this idea is called permuterm index. Okay, permuterm index. So let's see how we do this. So suppose that you have a term hello. Okay, you have a term, just when you index all your terms, right, in the dictionary, you have all these terms, right, the surface form of these terms. So in the permuterm index, you don't just index this term once, but you index all the variants of this term by rotating the words, the characters within the term, right? So here's how you do it. You index this term hello under all these different, basically you create many of these variants, okay? And then you index it under hello dollar, where dollar is a special symbol that indicates the end of a term. And then you can rotate this H to the back of the word, where you will get ELLO $H, right? And you further rotate the E to the back of the word, and there you get LLO $HE, and so on. Okay, so you keep doing these things. Okay, you keep doing these things, and then at the end of the days, you basically get these different, you index different, basically create these many different indices, okay, with this term. This term is not stored once, it stores this many times, okay? Now, when you have a query, X, okay, with no wildcard, okay, during search time, right? If the query is X without star, you just look up on this, okay? You look up for this thing, all right? So this is basically every word is indexed like this, right? In these different forms. So you look up X dollar, okay? So if you have X star, if your query is X star, you look up on this $X star, okay? So if it's $X star, basically for example, your hello, it will be something like this, okay? It will be here, okay? And if it's star X, then you look up for $X star. So the idea here is that whenever you see a new query, you always try to rotate it such that the star appears at the end. Okay? And by default, there's a dollar. By default, there's a dollar at the end of every term. Okay? Every query term. So like here, it's star X. So implicitly, there is a dollar sign here. All right? So all you need to do is to rotate. You need to rotate the star to after the dollar. So you will get $X star. All right? So if it's star X star, you will rotate this star to here, and two stars become one star. Okay? So it becomes X star. All right? And similarly here, what you would do is that you will rotate this thing, this X here, and then you rotate this star here, and then there implicitly there's a dollar sign here, and therefore it becomes this. Okay? So this part is a little tricky. Okay? All right. Now, this is an example. Okay? This is an example. Suppose your query is HEL star O. Okay, so if it's HEL star O, hello should match, right? Hello should match your query. So let's see if that is the case, right? So this thing here actually matches this example. Okay, so it's actually X star Y. All right. So by this example, you should rotate the X to after Y, and you put star after X, right? So therefore, you should look for this. Okay, you should look for this. And do you actually see it? Well, you can, right? If you search for this, then you can find this guy. Okay, you can find hello under this index. Okay, so basically every term is now stored in different index, such that depending on how you ask for hello, we will find this hello. Okay, that's the idea. All right, so now Chris, how do we handle a query like this? Okay, let's move on. So here's how you process the wildcard using the permuterm index, right? You rotate the query wildcard to the right, okay? Then you use a B tree to look up as before. But the problem here is that with the permuterm index, the lexicon now becomes quadruple the size, okay? Quadruple means that it's 4 times the original size. Why is that? Because this is an empirical observation due to the length, the average length of the words in English. Okay, so typically you will see 4 times the size of the original lexicon. All right, because every time you have a word, you have to create variants of that word. Okay, so on average, there will be 4 times the number of the number of variants will be 4. Okay, so that's why it quadrupled the size. Okay, so to sort of fix that problem, another approach is to use something called bigram, or in general, k-gram index. So the idea here is that don't enumerate it, but instead get the k-grams, okay? That is the sequence of k characters from each and every term, okay? And then index all these bigrams or trigrams. For example, if you have this text, right? April is the cruelest month. We can get the bigrams like this, right? The dollar sign indicates the start of a word, and also indicates the end of a word. Okay, so dollar sign is the boundary, right, of a word. So you would get dollar A, AP, PR, RI, and so on. Okay, and then what you need to do is that you maintain a secondary inverted index from bigrams to dictionary terms that match each bigram. Okay, so in other words, if you have a dictionary term, April, okay, so we know April can be broken down into these things, right? These things, okay? We will maintain a separate index so that whenever I see this, okay, there's a way for me to get to April. All right. Well, so whenever I see th, right, there's a way for me to get to month, and so on. Okay. So this is the bigram index, right? Here's an example. So if you have a bigram index, right? So this portion is this is the secondary index. Okay. Then this one gives you basically a list of all dictionary terms that contain $M. All right. So this is a list of terms that contains MO and so on. All right. So now, given this new index, right? How do we process wildcards? Okay. So suppose that you have a prefix query MON star. Now what you can do is that you take the MON star, okay, and you divide this thing MON into 3 different bigrams, right, which are the $M, MO, and ON. Okay, and then you run this query, you modify this query into this new Boolean query. All right, where you search for the terms this, you search for this, you search for this in the secondary index, right? And then you get all the terms that matches these 3 bigrams individually and intersect them, right? Okay, but of course, the downside of this is that you might, by doing this, right, you might incorrectly enumerate a word like this moon. Okay, because the word moon satisfies all these 3 search criteria, right? It starts with M, right? It contains MO, and then it contains ON, right? So you need some kind of post-processing to filter these terms against the query, all right? But again, like I said last time, once you get down to the intersection of these 3 sets, the end result becomes very small, and therefore post-filtering becomes feasible, okay? Even just linear filtering. Okay, so in general, using bigram or k-gram index is fast and space efficient compared to the permanent term approach earlier. All right, so if we are going to execute a Boolean query, okay, after that, right, after we have enumerated the dictionary terms and filtered out the incorrect ones, we will then do a Boolean query, right? So, but again, if you're going to have wildcards, you will still have like large number of disjunctions, like this thing, okay? So in actual fact, right, none of the commercial search engines allow you to search wildcards, okay? Wildcards are only possible on, for example, desktop search, okay, or some kind of enterprise search, right? And the reason for that is that it's still extremely expensive, okay? All right, so the next kind of tolerant retrieval I want to talk about is spell correction, right? So there are 2 principal purposes for doing spell correction. One is that there can be errors in the documents to be indexed, right? The other one is that the user query may contain some error, all right? So we want to correct user's query to match as many correct answers as possible. So there are generally two flavors in doing spelling correction. One is called isolated word, okay, which means that we do not consider the surrounding of the words. We do not consider the context of the word. Just by looking at this word itself, I know that this word is mistyped, Okay, so but the problem with this is that you will not be able to catch typos that actually is a correct word itself. Okay, for example, from and form, right? Both of these words are legitimate English words, but you may mistype from into form. Okay, so to fix that, another approach is context sensitive. That is, by looking at the neighboring words, we decide whether this word is mistyped or not, right? Like here, if I see I flew from Heathrow to Narita, okay, anybody who knows English knows that this form should be from, right? So that's the idea. We want to be able to catch this kind of typos. So just now I said, there are two kinds of corrections, right? One is to correct mistakes in the document. One is to correct mistakes in the queries. So correcting errors in the documents are especially needed when your documents are OCR. Okay, OCR means that you have a scan image, right? You convert the scan image into text. Okay, so this kind of correction are often tuned for errors like this. This is a strange error. Okay, so if you are familiar with OCR, you may see this kind of error. That is, I don't know what is this. Maybe it was room, okay, or something like that, or ruing. I don't know, but it looks like this, but it produces that because of the error in the OCR, it produces something strange. Okay, so to do this kind of thing, you have to use some domain-specific knowledge, such as you know that OCR can confuse O with D or 8 with 6, right? So you build some kind of statistical model that tells you that these two things may be mixed up. So let's try this and see whether the resulting word is a legitimate word or not. Okay, but um, not only that, not only OCR documents can have errors, web documents or even printed materials can have typos, right? Humans do make mistakes. So the goal is um, to make the dictionary as accurate as possible. That is, to avoid mistyped misspellings in the dictionary as much as possible. Okay, but often we do not change the documents, but instead fix the query document mapping. Okay, that is, we don't try to fix the document itself by changing the typos, but rather, if I know that this thing is actually room, right? If I know this is actually room, then I would just index this document under the word room rather than changing this document. Okay, so our principal focus here will be something like this. Okay, so this Alanis Morissette, I think it misses an R here. Okay, so this kind of typo, right? So we can either retrieve documents indexed by the correct spelling, or we can return a suggestion to the user that says, did you mean this, right? Did you mean that? I'm sure that you have experienced this kind of thing in your daily use of search engines, right? Some of the search engines does that. Uh, okay, so just as I said, there are two kind of approaches here. One is you can do correction on isolated words. Okay, the other one is you can do context sensitive words. So the fundamental premise here is that there is a lexicon that contains all the correctly spelled words. Okay, there are two choices. One is that you can use a dictionary, such as the Webster's English Dictionary, or you can use some kind of industry-specific lexicon. Like, for example, if you're handling medical terminologies, right? There is a medical dictionary. And then the second choice is a lexicon of the index corpus. Okay, in other words, I don't care so much about the actual standard English. All I care about is that I have this much data, this much document in my corpus, right? All I need to know is the words in this corpus. I don't have to know all the other words in the world. Okay, so if I do this, that means that I will treat everything in my corpus to be correct, including those mistyped words. Okay, and the advantage of this is that I can also include terms which are, special terms such as acronyms, such as names of persons, and so on, which are ordinarily not included in a dictionary. Okay, so I can do this. So given a lexicon, now that you have a lexicon and you have a character sequence Q, now the question is, the Q may not match any of the terms in your lexicon, okay, because Q contains an error, right? So now we're talking about isolated word correction, right? So how do you measure what is closest, right? You want to find the closest match in your lexicon to a query Q, okay? So there are a few alternatives to doing this, okay? So in this lecture, we are going to study 3 approaches. One is edit distance, one is weighted edit distance, and the last one is n-gram overlap. Okay, so these are the few measures to assess the closeness between 2 different words. Okay, so the edit distance is basically defined as given 2 strings, S1 and S2. Okay, what is the minimum number of operations to convert S1 into S2? Okay, and by definition, what are the operations allowed? Okay, there are only 3 very primitive operations, which are insertion, deletion, and replacement. Okay, so these basically what it means is that given one word, right, you can insert another character, you can delete one of the characters already in the word, or you can replace a character with another character. Okay, so so for example, if you have 2 words, the first word is DOF, and your second word is DOG. Okay, and the edit distance is 1. Because you just need to change F into G, right? And you get the word. All right, and another example is from cat to act. Okay, that's going to be 2. Okay, so why is it 2? Because you have to delete the C first, okay, and then you insert the C in between A and T, right? So that's 2. Okay, a 4th operation is called transposition. But transposition sometimes is not included in the standard edit distance. Transposition means that you can take that operation is actually 1 insert plus 1 delete, 1 delete and 1 insert together, which is you take a character, right, like C, and you insert it in here. You move it in here. Okay, that's called transposition. So if you allow this as a primitive operation, then the edit distance is just 1. Okay, now generally speaking, right, to solve this edit distance problem that is given to words, right, I want to know the minimum number of operations that converts one string to the other. You can solve that using dynamic programming. Okay, so you can check out this for like a nice example plus an applet on how to do this edit distance using dynamic programming. So I won't go into details on this. Okay, so another approach, which is like an improvement over the edit distance, is that we realize that when you measure edit distance over 2 strings, you are treating each operation equally. That is, each operation, no matter on what character, the cost is 1. Okay, so this is not the case in many real-world applications. In real-world applications, for example, the OCR, you know that certain characters are more likely to be mixed up. Okay, for example, I know that M is more likely to be mistyped as N as Q. Okay, that is from this to this. If you move from this to this, the cost should be smaller than changing M to Q. Okay, so if you have this kind of prior knowledge, then you could you could have adjusted the weight in the edit distance. Okay, and there comes this sort of variance of the original edit distance, which is called weighted edit distance. Okay, so basically here you would have a weight matrix that tells you if you do a certain operation from this character to this character, what is the cost? Okay, and given this weight matrix, you can adjust the dynamic programming and then handle the weights accordingly. All right. So once you have the edit distance, right? Given a query, you can enumerate all character sequence within a preset weighted edit distance, for example, 2, and then you can intersect the set with the list of correct words. Okay. So and then show these terms you found to the user as suggestions. So this is one of the approaches that search engines do. That is, you type a wrong word, right? So what I'll do is that I will take your word, okay, which is not in my lexicon, then I will vary it within two operations, okay, and then I use this new word to intersect with these new. I will vary it within 2 operations. There I will get a lot of different words, right? So I will intersect this set of words with the words in the lexicon, and if that intersection is not empty, that means I have found some possible replacement, right? I will show you these possible replacement and suggestions. As suggestions, I ask you which one do you think is correct, right? But alternatively, you can also look up all possible corrections in your inverted index and return all the documents, okay? But this is very slow, okay? Because you have to search your index multiple times, okay? Another simpler approach is that you can take the most likely correction. But again, this one requires some probability model. That is, you know which one is more likely, which one is less likely. All right. So this alternative approach disempower the user. That is, you do not take the user into the loop, right? You do not engage the user, okay? But it saves a round of interaction with the user. So some user might like it. I don't care about this. But the problem, also another problem with this is that you may return documents which are not relevant to the user, okay? Because you search many times and then you return all the results to the user. So given a misspelled query, right? Do we really have to compute the edit distance between this query and every dictionary term in our lexicon? No, we shouldn't do that, right? Because that is extremely slow. Okay, that is why previously I told you that instead of doing that, you should take the query and then vary the query by doing 2 operations, 2 edit operations on it, and then intersect that result with your lexicon. Okay, so another approach, instead of doing edit distance, right? Another approach is what we call n-gram overlap. Okay, so this can be used by itself for spelling correction. So what is n-gram overlap? The idea is that you can enumerate all the n-grams in the query string as well as in the lexicon. Okay, and then you use the n-gram index, which is what we learned a short while ago, right? To retrieve all the lexicon terms that match any of the n-grams. Okay, and then you set a threshold by the number of matching n-grams. Okay, so imagine that if your word, if the word that you type in is a correct word, then by taking the n-grams, right, every n-gram will have some match in the original dictionary. And if you take the intersection of those sets of matching terms, you will get exactly this term, right? But since you have a typo in it, so some of the n-grams is actually not right, okay? So as a result, when you do the intersection, okay, not all of them will match, right? So therefore, you need to set a threshold to return some of these. You need to set a threshold to find a term in the dictionary that matches your query the most by the number of overlappings. Okay, so here is an example, right? Suppose in the text, okay, you have a word November, okay, and this November will be indexed under all these trigrams. Okay, that is, you break it up into many different trigrams like NOV, OVE, VEM, and so on and so forth, right? And then basically this November will be indexed under all these different trigram index, right? Remember, each trigram index means that every trigram here is associated with a list of words, okay, that contains this trigram, right? And then now, when you have a query December coming in, you will also take the trigrams of this, okay? And then all you need to do is to try to overlap this set with this set, okay? And it turns out that the overlap are these three trigrams, okay? And the other trigrams don't match, right? So in order to measure how close this word is to this word, right? A naive approach is that you look at the percentage of the number of trigrams that match over the whole thing, right? Over the whole set of trigrams, right? So if that percentage is large, then you say, there's more match, right? If that percentage is not large, you say these two words don't look alike, right? So a principal approach to measure this overlap is what we call Jaccard coefficient. Okay, this is a commonly used measure for overlaps. Okay, so Jaccard coefficient is computed over two sets, x and y. Okay, and it's computed by the size of the intersection between the two sets. Okay, over the size of the union of the two sets. Okay, so now looking at this formula, right? If your x and y are exactly equal, then the result will be 1, right? If x and y have no overlaps, then the result will be 0. Okay, so now you can use this to measure the closeness between two words. Okay, in other words, you take the two words and you get the set of bigrams or trigrams from these two words, and then you compute Jaccard coefficient between the two sets. All right, if that coefficient is large, that means these two words look alike. Okay, if that is small, that means they don't look alike. Then you can take a threshold, right? For example, you can say 0.5 or 0.8. Okay, if the Jaccard coefficient is larger than 0.8, I consider this to be a match. Okay, otherwise it's not a match, right? Okay, so here's a basic example, right? So you have Lord, and if you look up the bigram dictionary, right, you will find all these things in here, and then you can merge the standard postings, and you can enumerate like this. Okay, so you will enumerate like this, and in the end, you can adapt this approach by using Jaccard or other metric. Okay, so the last portion that I want to talk about in the first class is that we can do context-sensitive spell correction. Okay, for example, I flew from Heathrow to Narita. All right, so this is in the text. And now if I have a query, flew from Heathrow, I would like to respond that did you mean flew from Heathrow? Okay, because no document matches the query directly. Okay, so in order to do that, we have to look at the surrounding context. Okay, our first idea is that we can retrieve dictionary terms close in terms of edit distance to each query term. Okay, and then we can try all possible resulting phrases with one word corrected at a time. Okay, that is, given that the fact that you asked for flew from Heathrow, right? I will take every word in your query and try to vary it a little bit. I vary it in such a way that it becomes a correct word, right? And then I search in my document to see how many hits do I have in my index? Okay, if this corrected query returns a lot of hits, then this is more likely to be a correct correction, okay, of your original query. Okay, the quiz. So consider that for flew from Heathrow, we have 7 alternatives for flew, 19 for from, and 3 for Heathrow. How many corrected phrases will you enumerate in this key? Okay, let's carry on. So another approach to doing the context-sensitive retrieval is that you can break your phrase query into a conjunction of byword. Okay, so bywords. Then you look for bywords that need only one term corrected, and you enumerate only phrases containing common byword. Okay, so this is like a slight modification from the previous one where we only consider one word at a time, right? So this one you consider 5 words, 2 words at a time. Okay, so generally speaking, the approach here is that you need to enumerate many different alternative possible corrections, okay, for the did you mean question, all right? And you need to figure out which to present to the user, and generally speaking, you want to present an alternative that has the most hits, okay? So for this one, you may need to do query log analysis. That is, according to the historical queries by the users, I know that certain query returns the most hits, okay? Certain queries has a lot of documents returned and so on and so forth, right? I don't need to actually go to my index and return the documents, but rather I can like do some statistical counting beforehand, right? So that during runtime, I can quickly know this query is going to produce this many hits, this query is going to produce this many hits, and so on. Okay, so more generally, you can model this as a ranking problem, right? So you can rank your alternatives by a probability model, probability of correction. This is the corrected string given the original query. Okay, so this one, you want to maximize this probability, okay? And from the base rule, this can be converted into probability of the query given model times the prior probability of the correction, okay? And there are some terminologies for this. This part is called the noisy channel, and this is called a language model. It's called a language model because this gives you basically the prior probability of all the correct terms in your lexicon, in your dictionary, right? This is like, for example, from is more likely to appear in the documents than form, okay? From prior probability maybe 0.01, the other one is 0.001, so, okay? So that's a language model. Okay, so the last topic I want to say is soundex. Okay, so the idea is that you want to be able to expand the query into an equivalence class of words that sound similar to the query. Okay, for example, if you have Chebyshev, okay, if you have the word Chebyshev, you want to be able to return documents that contain this Chebyshev that has different spelling but similar sound. Okay, So this is actually a very old technique, the Soundex, okay, invented for the U.S. Census, primarily for persons' names, because very often people have aliases, okay, or different spellings for the same name. So a typical algorithm for the Soundex is like this, okay? You turn every document to be indexed turn every token to be indexed into a 4-character reduced form. Okay, every token to be indexed is converted into a 4-character reduced form. Okay, you do the same. So this is a little bit like hashing. Okay, so it's like you're hashing many different terms into a smaller set of terms. Okay, so if 2 terms are hashed into the same reduced form, then these 2 are considered equivalent by Soundex. Okay, so but how do you do this? Okay, this is the algorithm. It's very interesting that we can do this pretty simple. Okay, so you first, given a word, you retain the first letter of the word. Okay, and then change all occurrences of the following letters to 0. Okay, basically any vowels, A, E, I, O, U, plus H, W, and Y. These are silent characters, right? So change all of these into 0. The vowels and the silent sound are 0. Okay, and then you change the letters into digits according to these groups. Okay, that is whenever you see B, F, P, V, change to 1. C, G, J, K, Q, S, X, Z change to 2. Right, and the reason for this is that in English, these things may sound similar. Okay, they may sound similar, right? So you do this. After you do this, okay, you continue, right? You remove all pairs of consecutive digits. Why? Because if you have consecutive digits, right? Okay, wait a second. So consecutive digits means that if you have a pair of digits that are next to each other, right? Digit means that it's the numeric digits, okay, numeric digits. And then you remove all zeros from the resulting string, and then you pad the resulting string with trailing zeros, and if it's less than 4 letters, okay, because you need to produce a 4-letter term, okay, so if it's less than 4 letters, you need to pad the resulting string with trailing zeros and return the first 4 positions, which will be of the form uppercase letter, digit, digit, digit. Okay, so if you take Herman as an example, right, you'll keep this, right, and then this becomes 0, this becomes 0, right, and these and this, I forgot, maybe this is 6, right, this is 5, 0, and so on. So in the end, you will get this H655. Okay, so and if you go back home, you follow this again, right? You will realize that this Herman will give you the same code. Okay, so therefore these 2 sound similar, right? So how useful is this Soundex? All right. In the end, it's not that useful for information retrieval because primarily this is designed for humans, for persons' names. Okay, it is only useful for persons' names. Okay, and also because you are reducing everything to 4 characters, right? So there's a high chance of mixing things that don't sound the same together into the same bucket, right? So this is okay for high recall tasks. For example, if you're police, right, and you heard something over the phone conversation, a person's name, right? You want to enumerate all possible names that sound like that, okay? So this will give you that, okay? It will give you more than what you need, right? So that's why I say this is high recall task. right? Other people have already shown that there are other more sophisticated algorithms that can perform much better in the context of IR. Okay. So far, we can handle fault tolerant, tolerant retrieval tasks, such as the following, right? We have a positional inverted index with skip pointers. Okay, this is what we learned last time, right? Now we can have wildcard index, we have spell correction, we have soundex, so everything together. Now we can answer sort of this kind of complicated queries, like spell Morissette means that I'm not sure about the spelling, right? So this is spell Morissette means that give me all the words that spell similar to this, right? And within 3 characters this is a wildcard query, right? Or soundex Tchaikovsky, okay? So give me things that sound similar to this Tchaikovsky, okay? So we can handle complex Boolean queries, Boolean tolerant queries like this, okay? All right, so that's it. Let's take a 10-minute break. Okay, so far we have sort of learned the general process of how to do tolerant retrieval, right? That is, you want to be able to answer queries that are not exactly right or doesn't exactly match the documents, right? Okay, now let's get into a more sort of a system-C issue here. That is, how do you actually construct the index? Okay, so previously we have learned what is the data structure for the dictionary, right? We discussed the pros and cons of hashing versus trees, okay? And in general, we use the trees because we want to handle multiple tolerant retrieval problems, such as prefix search, search involving wildcards, and so on, right? So in this class, we are going to learn how to actually construct this inverted index. Okay, so there are some issues with this. The thing here is that you have limited amount of memory. Okay, so the best thing to do is, of course, to keep your entire index in memory so that you can answer queries very quickly, right? But that is not possible in real world situations. So given that you have limited amount of memory, right, you need to make design decisions in information retrieval based on the characteristics of your hardware. Okay, so let's start by looking at some basics in hardware. Okay, so as you know, accessing the memory is much faster than accessing the disk. Okay, so when you want to read certain amount of data from the disk, it involves 2 operations. One is seek, one is transfer, right? So the disk seeks usually involves moving the disk head to a relevant area on the surface of the disk. Okay, so that usually is amounts to protracting or retracting the arm to the right track of your disk, right? So that takes some time, but it doesn't contribute to your data, right? It doesn't actually read the data. Once the read head is on top of the correct track, then you have to wait until the relevant data rotates underneath the head, and then you start reading, right? So all that is so-called seek time, okay? And that time is actually wasted, so to speak, because you're not transferring the data. Once the data is underneath the head, then you start transferring, okay? That is the meaningful time, all right? So when we do disk I/O, right, we want to avoid the disk seek time as much as possible, okay? So in other words, you don't want to read many small chunks of data. If you want to read many small chunks of data, you got to keep moving the disk arm, okay, and keep seeking and not transfer. So that is a waste of time. So rather, you want to read one large block at a time. So that is what we mean by block-based disk I/O. Okay. So typical block size varies from 8 kilobytes to 256 kilobytes, all right, depending on your operating system and the application. So the servers using IR system now typically have large amount of memory, okay, tens of gigabytes, okay, but the available disk space is still hundreds and thousands times larger than the memory, okay. So fault tolerance is very expensive. That is, if you want to build a fault tolerant system, okay, that can handle any kind of failure, power failure, all sorts of outage, right? That is very expensive. So rather you go for many cheap machines, okay? And by doing sort of redundancy, okay, on these cheap machines, it's more economical than buying one single fault tolerant machine. All right, so for this lecture, we are going to make the following assumptions, okay? We denote S as the average seek time, okay? Which is usually, for example, 5 milliseconds, okay? And we denote B as the transfer time per byte, okay? And that usually takes 2 times 10 to the power minus 8 seconds, or 0.02 microseconds. And the CPU's clock rate is usually 10 to the 9 seconds, okay, or 10 to the 9 seconds, 1 over 10 to the 9 seconds, okay. So the lower part, the P is a lower level operation, such as a compare and a swap of a word, right? So the size of the memory is assumed to be several gigabytes, and the size of the disk is assumed to be 1 terabyte or more. Okay, so our example corpus for this purpose is called RCV, which is much larger than the Shakespeare's collection of works. Okay, so the collection that we use isn't really large by any industry standard, okay, but it's large enough for us to do some to have some feel over how to retrieve from a document collection. So this RCV1 is 1 year collection of Reuters Newswire, okay, part of the 1995 and 1996 news, okay. So this is what a RCV1 document looks like. Okay, it contains a title of the news, date, time, and then the body of the news. All right, so that's what it is. Okay, so here are some statistics of the RCV1 dataset. All right, there are 800,000 documents in total. Okay, and that number is denoted as N, and we denote average number of tokens per document as L, which is 200 in this case. Okay, there are 200 tokens per document. Right? So the number of terms, okay, in the document set is 400,000. Remember, the terms is the distinct tokens. Okay, distinct tokens. So the average bytes per token is 6 with the space and punctuation, and without a space and punctuation is 4.5. Average number of bytes per token is 4.5, and the average number of bytes per term is 7.5. And there are 100 million non-positional postings. Okay, non-positional posting means that we don't care about where the word appears in the document, but just the fact that this word appears in some document. Okay, so we just record a document ID. Okay, so one thing that might raise your eyebrows is that the total number, the average number of bytes per term is 7.5, which is larger than the average number of bytes per token, which is 4.5. Why is that? You know why? Why the distinct, basically the average length of a distinct term is larger than the average length of a token in the document. You know why? Yes, correct. There are many, many shorter tokens. Okay, the longer tokens are rarer. Therefore, if you look at the distinct, right, tokens, this this number is larger. Okay. Okay, so recall how we construct the index last time, right? So we take the two documents, lemmatize it, and then form a list of all words and the document ID that they appear in. Then we sort it, right? We sort it like this, and then after that, we will get the so when we build index, right, we parse the document one at a time. Okay, so while building the index, we cannot easily exploit compression tricks. Okay, so we will talk more about these compressions later on. Okay, so the final postings for any term are incomplete until the end. That is, while you are building this, right, you incrementally add postings to each and every dictionary terms, right? So the postings wouldn't be complete until you have finished going through all the terms, all the tokens in your documents. Okay, so uh, so the posting entry, earlier I showed you that, right? So if you have term, document, and postings, right? So the posting entry, we assume that it takes 12 bytes, okay, per posting entry, for non-positional posting entry, okay, which consists of the term, document, and frequency, okay? So if you have large document collections and large number of terms, it takes up a lot of space. Okay, in the case of the RCV1 document set, we have in total 100 million documents. Okay, so this is okay. If you want to store this in memory, this is okay in 2009. Okay, but the real collection will be much larger. So therefore, we have to resort to not only storing things in memory, but also store part of the index on disk. Okay, so how do we store the index on disk? Okay, can we sort data on disk like the memory? Well, it's not so trivial, right? It's not so trivial to do that. So we can use the same index construction algorithm for large collections, okay? But how can we do that? By using the disk instead of using memory, okay? So as you know, if you want to sort 100 million records on disk, that'll be very expensive, right? Because when you do sort, you need to compare, right? And every time you do compare, you need to do seeks, okay, between two different blocks. So that's very expensive. And therefore, we need an external sorting algorithm, okay? So I'm sure you guys have taken these database course before, right? So if you have taken database course before, you should have learned external sorting algorithm, right? So this is basically it. So the bottleneck here is that we parse and build posting entry one document at a time, and now we sort posting entries by term, and then by document within each term, okay? So doing this with random disk seeds will be very slow, okay, because it involves sorting 100 million records. All right, so this is just a question, right? So if every comparison involves two seeks, right, and n items could be sorted using n log n comparisons, this will take how long? But obviously it takes a long time, right? So one potential fix to this is to use a scheme called blocked sorted base indexing, or BSBI. Okay, so you can do this and sort using fewer number of disk seeks. Okay, so assuming that you have records that takes up 12 bytes, okay, 4 bytes for the term, 4 bytes for the document ID, and 4 bytes for the frequency. All right, 4 bytes for the term, because just now I said that the term on average takes up this much, okay? And they are generated as we parse the document, right? Because as you parse the documents, you decided, I have seen this term in this document, so I need to generate a new posting, right? So you must sort 100 million such 12-byte records by term, okay? So we define the idea of blocks, okay, which is roughly equal to 10 million such records. So we divide our 100 million into blocks, okay, basically divided into 10, 10 blocks. Okay, so the basic idea is that you accumulate the posting for each block, sort and write to disk, and then you merge the blocks into one long sorted order. Okay, that is, instead of sorting everything together, right, you divide it into chunks and you sort within the chunks. Okay, and then you output the sorted elements into sort of, you merge the sorted elements together and then do the sorting as you merge, right? So this is similar with what you learn in your database course, okay? So generally speaking, right, this is the chunks, right? These are the different blocks. So once you sort the blocks, then you merge them, right? And it becomes something like this, okay? So this is the general approach, right? So it's actually similar to what I said, so I won't repeat here, okay? But generally speaking, you need 2 copies of data on disk, okay? But you can optimize this. Okay, so this is the algorithm pseudocode for doing BSBI. Okay, so how do you merge the sorted rows? Okay, you can do binary merges, okay, with a merge tree of log 10 to the base 2. Remember, you have 10 rounds, right? You have 10 rounds going, right? So you can merge 2 at a time, and then merge the intermediate one into another layer, and you keep doing this, right? So it's a tree, right? It's a merge tree. So during each layer, you can read into memory the rounds of block 10, the 10 million records. Okay, so assuming that 10 million can fit into the memory, right? You merge and then you write it back into the disk. Okay, so this is your disk. You read it into memory, you merge them, and then you return it to the disk, right? So all this is quite trivial. Okay, so but it's more efficient to do multi-way merge, right? Rather than doing 2 at a time, you can do n-way merge at a time. Okay, provided you can read decent sized chunks of each block into memory and then write out a decent sized output chunk. Okay, then you can do this without killing the disk. All right, so the remaining problem is that our assumption here is that you can keep the dictionary in the memory, okay, because you need the dictionary in order to implement a term-to-term ID mapping, right? Remember, you need to, one of the elements of the posting is a term-to-term ID pointer, right? So you need that mapping, therefore your dictionary must be in the memory. But this intermediate files can become very large, okay? So you would end up with a scalable but very slow index construction method. So an improvement over that is called SPMI, or single pass in-memory indexing. Okay, so there are 2 ideas here. One is that you generate separate dictionaries for each block. All right, instead of having one universal dictionaries, you create dictionaries for each block. Okay, each of the 10 blocks, and you don't sort, but just accumulate the postings in the posting list as they occur. Right, as you see more and more terms in your documents, you just create more postings without sorting them. Right. So with this idea, then you can generate a complete inverted index for each block, and these separate index can then be merged into a bigger index. All right. So this is just the idea. So this is I think this is for your information, right? It's not that interesting. So the merging of the blocks will be analogous to BSBI that I talked about earlier. Okay, so you can take compressions, you can do compressions over the dictionary terms to make SPMI even more efficient. So I would talk about compression of the terms as well as compression of the postings. You can compress both, right? In the next class. All right. So for real world web scale indexing, not only you have to keep the index on disk, you may also distribute it over a different locations, right? So in that kind of situation, you need a distributed computing cluster, okay? Individual machines are fault prone, okay? But collectively, right, you want to achieve some level of fault tolerance, okay? So how do you exploit such pool of machines? Okay, imagine that you have large web search data centers, you know, by these big search giants, okay? Generally, they contain large number of commodity machines. So they deploy such data centers around the world. For example, by estimate, Google has 1 million such servers, 3 million processors and cores in the year 2007. And now this number may be much more than that. So massive. So if you have large scale, massive data centers, there's this issue of uptime and downtime with your machines, right? So in a non-fault tolerant, if you're non-fault tolerant machine, right, non-fault tolerant system with 1,000 nodes, and each node has 99.9% uptime. Uptime means that 99.9% of the time is up and running, right? But there's a 0.1% chance that it's down. Okay, then what is the uptime of the entire system? Okay, so this is, well, the answer is 37%. Okay, so you figure it out offline later. Why is 37%? Okay. All right, see, here is a quiz. If you have a server that will fail after 3 years, for an installation of 1 million servers, what is the time interval between machine failures? So when we say this machine fails, that means if any of the machine fails, okay, then the whole thing is considered failed. So if you have a server, suppose every server failed after 3 years on average, and if you have 1 million servers, what is the time interval between these failures? This is a little tricky. Okay, let's move on. All right, so if you want to deploy a distributed indexing, again, this is for your knowledge only, okay? So generally speaking, you need a master, okay? So this master will orchestrate all the indexing jobs, okay? And this master is considered fail-safe, which means it never fails, right? In reality, that's not possible, right? But you could invest a lot of money in this one machine, right, and make sure that it's very steady. And you break up your indexing task into a set of parallel tasks. right? And then the master will assign each task to an idle machine from a pool. Okay, so you have a pool of machine, right? So every machine that is free will go and grab a piece of Java and work on it. We will use two sets of parallel tasks. One is parsers, one is inverters. So the parsers essentially takes a document, right, and tokenize it, and then get the unique terms from there, right? That's the parsers. And then the inverters will basically create the postings, right, based on the terms discovered in the document. So we will break the input document collection into splits. Each split is a subset of documents. Okay, and this corresponds to the blocks in the two approaches, BSBI and SPI-MI that I talked about earlier. Okay, so what does the parser do? Well, the master will assign a split to an idle parser machine, right? So remember, the split is a set of documents, right? So the parser reads a document at a time and emits the term document pairs. Okay, so essentially it scans through the documents and it takes out all the unique terms and it returns you the term document mapping, right? The parser writes the pair into J partitions, and each partition is for the range of terms' first letters. For example, if I want to partition it into 3 partitions, right, I could write it into partition 1 if the term starts with a letter between A and F, right? Write to partition 2 if the first letter is between G and P, and so on. Okay, and then the inverter will take it from there. Okay, and the purpose of dividing this partition is to promote parallelism, right? So that the inverter can, oops, what is this? This one. Okay. So that the inverter can collect the pairs from different term partitions, sort and write to the posting list. Okay, so that's what the inverter does. Okay, so this is a general architecture of the data flow of the distributed index. All right, so you have all the splits here, right, where each split represents a document set, and each of this document set is fed into a parser, right, which will then generate the term document mappings and divide them into 3 partitions. Okay, and then the inverter would then take the mapping from a designated partition. For example, if you have 3 inverters, right? Remember just now I said the K is 3, right? If you partition the thing into 3 partitions, you will have 3 inverters to work on these partitions. So this first inverter will take care of mappings coming from A to F from all these parsers. Okay, and inverter number 2 will take care of the mappings coming from partition G to P. Okay, so as a result, each of these inverters will write postings to different part of the index, basically. Okay, so these postings are for A to F, these postings are for G to P, and so on. Okay, so this process can be distinctively divided into 2 phases. The first phase is called the map phase, okay, where you basically map different splits into different parsers. So it's like you're dividing the job, right? And then you assign it to different parsers, right? And then different parsers work on it and get some results, right? And then the second phase is called the reduce phase. So in the reduce phase, each inverter will collect intermediate results from the different parsers, right? And merge them, sort of merge them together and get the posting list. Okay, so this is called the reduce phase. And this is actually, this idea is basically an algorithm we call MapReduce. Okay, so MapReduce, designed in 2004, is a robust and conceptually simple framework for distributed computing. Okay, so this thing was first used in the Google index system, okay, as consisting of a number of phases and each implemented in MapReduce. So the index construction was just one phase. Okay, another phase is to transform an index partition in term partition index into document partition index. So just now remember, the end result of the index construction was that we have postings associated with different partitions of the terms, right? So that's called term partition index. Okay, another second phase will be to convert that into a document partition index. Okay, in the term partition one, each machine handles a sub-range of terms. In the document partition index creation, one machine handles a sub-range of documents. Okay, so later on, as we will discuss, right, in this course, most search engines use a document partition index rather than term partition, okay, for better load balancing and so on. So I will explain this later on in the course. Okay, so this is the general scheme for doing MapReduce in index construction. Okay, so generally speaking, your map function takes an input, right, and then reduce a list of key value pairs, right, and the reduce function will take a k, different case, right, and the list associated with that k, okay, and then essentially merge the list, all right, into an output. All right, so this is the idea, and this is a generic sort of signature of the map and reduce function, and we instantiate that into the index construction problem. The input becomes a document collection, right? The output of the map is now a list of term ID and document ID, and the reduce basically takes a number of mappings. The term mapping, reduce function actually takes a term and the list of document ID, another term, a list of document ID, and it returns you a number of posting lists for each term, right? For each term ID, you have a posting list. Each term ID, you have a posting list. Okay, so this is the conceptual schema, right, for doing MapReduce on index construction. Okay, so here's an example, right? So you have two documents, right, like this. The map function essentially will create a lot of these mappings, right? And the reduce one will actually merge the mappings for a particular term. Okay, so for example, this one, C is a term, right? So these are the documents for C. Died is a term, this is a document for this, and so on and so forth. Okay. So far, we've been assuming that the document collections are fixed and static. Okay, but in reality, documents do change over time, right? There are new documents that needs to be inserted. Some documents needs to be modified or deleted. Okay, this means that at the same time, the dictionary as well as the posting list needs to be modified as well. Okay, so when you have a new term coming in, right, you may need to add new terms to the dictionary, and then the postings may need to be adjusted for terms that are already in dictionary, right? Suppose you have a new document coming in, all the terms you have seen before, right? All the terms are already in the dictionary, but then because of this, the existence of this new document ID, you need to insert this document ID into the various posting lists. So the simplest approach will be to maintain one big main index, right? And all the new documents will go into smaller auxiliary index. That is the fixed. Suppose you already have a document collection, right? And you have already built an index. That is your main index. Okay? So as you have new documents coming in, you build smaller auxiliary index based on those new documents and keep them separate. All right? So when your query comes in, you search both the main index and the small auxiliary index, and then you merge the result together and present to the user. Okay, so this is the naive approach. And for deletions, right, if you want to delete some documents from your document collection, you need to create an invalidation bit vector. So assuming that you have 1 million documents, right? So this document, so this invalidation bit vector will be 1 million bit long. All right. Any document that's deleted from your document set, you will set 1 on that bit, on the corresponding bit in the vector, right? So now, when then what you do is that you do the normal thing, right? You do your normal search and query if a query comes, right? So you will return a set of documents, right? Then you will end that document with this invalidation bit vector. Anything that is 1, right, will be filtered out, and you will not return that document. That's the idea, all right? So periodically, you may need to re-index all the auxiliary indexes into the main index, all right? So this is the naive approach. The problem with this is that if you have a lot of, let's say you have a lot of dynamic changes to your documents all the time, it's not very good, right? If you have a lot of such mergers, you will touch a lot of stuff. That is, you do re-indexing a lot, so the performance will be degraded. Okay. Actually, if you merge the auxiliary index into main index, and if you keep a separate file for each posting list, merging is actually quite simple. You just have to append the posting list to the corresponding words, okay, to the corresponding postings in the main index. But this will basically requires us to have a lot of files, so it's inefficient for OS, right? As you know, OS has a sort of a limit, as in how many files can be opened at the time, right? At the same time. So the assumption for the rest of this lecture is that the index is one big file rather than many small files. Okay. In reality, you could use a scheme somewhere in between. That is, whenever you have index file whenever you have posting list that is too big, you split it. Okay. So, and then you can collect those posting lists that are small into one file. Okay. So that will be a scheme like striking a middle ground in between. Okay, so another thing that you can do is called logarithmic merge. Okay, so you can merge. Basically, you can keep your index like a series of indices, each twice as large as the previous one. Okay, so at any one time, some of these power of 2s are instantiated. So you keep the smallest index called Z0 in your memory, and the larger ones are on disk. Okay, so if your Z0 becomes too big, then you write this into disk as I0 or merge with the I0 if I0 already exists, and then write the merger to I1 and so on. So it's like whenever the thing becomes too large, you write it to disk. Okay, then you start a new one in your memory. All right, so this is called logarithmic merge. So the index construction for the logarithmic merge, right, is quadratic. Okay, is order t squared, as each posting is touched in each merge. So, sorry, this is the first one. This is not the logarithmic merge. This is the auxiliary and main index merge, right? So if you have a main index, all right, and you want to do a merge between your auxiliary index and the main index, the time complexity is roughly t squared, all right? So if you have a logarithmic merge, then each posting is merged the order log t times. Okay, so the complexity is t log t, right? So this is smaller than using the main index and auxiliary index. So in other words, logarithmic merge is more efficient for index construction. Okay, but now the downside is that the query time requires merging of log t indices, right? Because now you have like a tree of you have increasingly small indices, right? So every time you answer a query, you have to merge the result from these individual queries together. So that involves merging log t index. Whereas if you just have one main index and one auxiliary index, that takes just constant time. All right. So the trade-off is how many index you have, right? If you have more indices, the construction time is less, but the query time is more. Okay. So there are other issues with multiple indices, right? So if you want to collect the statistics of your entire document collection, and if you have multiple indices, then you have to go through all these index, right, to get, for example, what is the frequency of the a particular term, right? Previously, if you have just one index, you can directly get that number. Now you have to go through many different index and sum it up, right? And another thing is that when we speak of the spelling correction, right, which of the several corrected alternatives should we present it to the user? That depends on the frequency of use, right? That depends on which which corrected alternatives can produce better results, right? More results, etc. Right? So for that, you need to collect statistics. Okay? So, so how do you maintain the top ones with multiple indices and invalidation bit vector? Well, one possibility is ignore everything but maintain the main index for such order. In other words, you're using the main index as your sample. Okay? You are assuming that the statistics that you collect from the main index represent the entire document represent the whole set of indices. Okay, that's the idea. So we will see that such statistics will be used in the results ranking later on when we talk about rank retrieval. Okay. So what happens with dynamic indexing? That is, as your document changes, right, you need to keep modifying your index. This is the case with large web search engines. Okay, so these engines actually do this kind of dynamic reindexing all the time. Most of the time, their index have frequent incremental changes. For example, new items, new web pages, right? For example, Donald Trump now is popular, right? You see a lot of these things. So you have to reindex the documents related to Donald Trump, right? But sometimes they're also periodically reconstruct, because as I said, this kind of thing is like you try to balance it, but after some time the thing becomes so skewed you have to reindex everything from scratch. Okay, and that is the time when you experience some significant delay when you're using the service. Okay, for example, Google, back in the year 2008, there is a terminology called Google Dance, which means that during a certain period of time, you search the same query in Google, you get very different results. So the behavior of the search engine varies a lot during a short period of time. That's because Google is doing the reindexing at that time. Okay, so this is called Google Dance. And this happens to other search engines as well. Okay, but nowadays you see this less and less because Google is handling this better. Okay, handling the reindex issue better. It has some backup thing that handles all the reindexing and only take it online when it's ready and so on and so forth. Okay, so it's doing more sophisticated stuff. So there are other sorts of index, right? So far we've been talking about non-positional index. That is, the index contains only the word and the document ID, right? But remember, we also have this positional index, right? If you want to handle range queries that ask about that involves phrases, right? Then you have to do some additional stuff, right? So for positional indices, you can use the same sort of sorting algorithm like before, only that the index is larger, right? Because you contain more things in that index. For n-gram index, right, you will have to enumerate the n-grams, and then for each n-gram, you need pointers to all dictionaries containing this n-gram, right? So in order to effectively look for the same posting entry, you will need to, because this thing happens repeatedly in parsing documents, you need efficient way to hash, right? Efficient hashing to keep track of what is a identical and same posting entry, okay? So for example, the trigram UOU occurs in the term this, okay? On each occurrences of deciduous, okay? Because UOU happens in here, okay? But you only need to process each term once, okay? But there are many occurrences of such term in the document collection, right? So you need a way to hash it, to quickly hash it to the right posting entry. Okay, guys, let's continue. So just now we talked about various schemes to do index construction, right? So the idea is that when you have constraints with hardware, right? How do you make good use of your memory, right? And then how do you make use of the disk and still being able to do sorting and merging and so on, right? And then we talked about how to do distribution onto different machines. But one issue that is always there is that even if you have all these distribution strategies, map and reduce and everything, right? It boils down to the fact that your index contains two parts, right? You have the dictionary and you have the postings, right? No matter where you store these two things, they are there, right? So the problem is that if your dictionary gets very large, your posting list will also be very large, right? So if there's a way for us to contract the dictionary, to compress the terms in the dictionary, and also to compress the postings, it's beneficial to us, right? No matter how. So next we're going to talk about how to compress the dictionary and how to compress the postings, okay? So in general, right, once you compress the dictionaries and the postings, you use less disk space, right? And it is possible that you can keep the entire dictionary in the memory, okay? That will speed up your process, okay? You can also increase the speed of disk transfers if you compress stuff, okay? The idea is that if you read compressed data and then decompress it, that is faster than reading uncompressed data directly, okay? But of course, that idea works only if your decompressing algorithm is fast enough, right? So for dictionaries, right, if we can compress it, we can keep it in the main memory, okay? So if it's small, if your dictionary is kept as small as possible, you can even use part of your memory to store the posting list, right? So that it's just like you're making some space for the posting list. And if your posting files are small enough, you will reduce the disk space required, and you will reduce the amount of time needed to read posting files into disk, from disk, okay? So large search engines keep a significant part of the posting in memory, right? So compressing the postings allow you to do that in memory, right? So we will devise some IR specific compression techniques in this class. So again, let's recall the statistics of our collection, data collection, right? RCV1. So assuming that we have a document collection of 800,000 documents, and the average number of token per document is 200, The number of terms, unique terms, is 400,000. The average number of bytes per token without space and punctuation is 4.5. The average number of bytes per unique term is 7.5. And there are 100 million non-positional posting. Okay, so before we go into the specific techniques, right, there's one thing I want to make clear to you, which is the definition of lossless versus lossy compression. Okay, by lossless compression, that means we preserve every bit of information. No information is lost. Okay, this is what we usually do in IR. Okay, we don't want to lose any information. For lossy compression, we discard some information. Okay, this is the case in image processing, right? When you do image processing, it is okay to lose, or audio processing, right? It's okay to throw out some of the bits and still being able to use the content. So there are several pre-processing steps in the IR that can be thought of as lossy compression. For example, when you do case folding, right? You reduce all the uppercase to lowercase. That can be thought of as lossy compression. When you remove the stop words, when you do stemming, these steps can be thought of lossy. But other than that, mostly our compression techniques that I'm introducing next in this class are considered lossless. Okay, so so let's look at the situation of our task here. Okay, first, how big is our vocabulary? Okay, so in other words, how many distinct words are there? Can we assume an upper bound? Okay, why do I care about that? Well, because if I want to store the dictionaries, right, I want to know how many bits I need to store each distinct words, right? So if I know that there is an upper bound, then I can take the log, right, of that, and then that's the amount of bits I need, right? So, but the reality is that not really, okay? So if you think about it, right, the one that we just looked at, it's something like this, okay? So there are 10 to the power of 37 different words of length 20. This is a huge number, okay, from the documents that we have. So of course, this is the worst case, okay? This is the worst case, okay? But in practice, the vocabulary will keep growing with the collection size. Okay, what does that mean? That means depending on the size of your collection, you can estimate what is the size of your vocabulary. Okay, so this is important. We want to know that what is the relationship between the size of your vocabulary and the size of your document collection. Okay, so there's one empirical law that governs this relationship between the vocabulary size and the collection size. And this law is called the Heap's law. Okay, so Heap's law says that the size of the vocabulary is proportional to the kth power, the bth power of the size of the document collection. So this t here, n is equal to k times t to the power of b. Okay, n is the size of the vocabulary, the total number of distinct terms, right? And t is the total number of tokens in the document collection, right? And the k and b are parameters, okay? Typically, k is between 30 to 100, and b is usually 0.5, close to 0.5, okay? So if you look at this thing, right? If you take the log on both sides of this equation, what do you get? You get log n equal to b times log t plus log k, right? Okay, that's what you get. So once you do that, and because b is nearly half, right? So if you plot this line, right? You plot the log line of this thing, you notice that it's something like this. This is the actual empirical line. Okay? And this line is the theoretical line. The theoretical line is that once you take the log on both sides, right, it's actually a linear relationship between log m and log t, right? So, and the slope of this line is roughly half, okay? Because b is roughly equal to 0.5, okay? So in reality, from our corpus here, right, if you really plot this, okay, from our corpus, you know that this b is 0.49, which is roughly equal to that. This is the closest fit. Okay, we try to fit a linear function on that, and this is the closest fit. Right? This is 0.49, and this is the k, log k. This is the log k. Okay, so k is equal to 10 to the power of 1.64, which is roughly equal to 44. Okay, and b is equal to 0.49. Okay, here's a quiz. Remember, b is roughly equal to 0.5, k is 44 in the previous case. Okay, let's continue. Okay, so the Heap's law gives you the relationship between the size of the vocabulary and the size of the document collection, right? We also want to know the relative frequencies of the terms, okay? So you have all these distinct terms, right? Different terms may appear different number of times in the document, right? So we want to know how frequent a term would appear in the document on average, okay? In natural languages, there are a few very frequent terms and many, many very rare terms, okay? So there's another law which governs this relationship, and this is called the Zipf's law. The Zipf's law tells you that the ith most frequent term has frequency proportional to the reciprocal of I. the inverse of I, okay, 1 over I. In other words, the CFI means the term frequency, okay, of the I most frequent term is proportional to 1 over I, okay, or is equal to K over I, where K is a normalizing constant, all right? So CFI is the collection frequency, that is the number of occurrences of term TI in the collection, okay? Remember, I is the rank, okay? I is the rank of the term, all right? So in other words, if the most frequent term, okay, for example, okay, happens CF1 times, because it's the number one most frequent term, right? Then the second most frequent term occurs CF1 divided by 2 times. The third one occurs CF1 over 3 times, and so on. Okay, so this equivalently, since CFI is equal to K over I, right? If you take log on both sides of this equation, you get log CFI equal to log K minus log I. What does that mean? That means there's a linear relationship between log CFI and log I, right? So this is another power law relationship. Okay, similar to the Heaps law, this is another power law relationship. Okay, which means if two things, you take log on both sides, right? If there's a linear relationship, this is a power law relationship. Okay, so this is the plot of the Zipf's law for our RCV1 dataset. Okay, the x-axis is the log of I, the y-axis is the log of CFI. All right? Okay, so you see that there's this relationship. Okay, now let's now having talked about these fundamental basics, right? And the reason why we talk about these things is because for information theory, right? So you need to know, you need to be able to estimate the size and the frequency, right? We want to know the size because we want to compress the dictionary of the terms, right? We want to know the frequency because we want to also compress the postings, okay? So now let's consider compressing the space for dictionary and posting. Okay, we're assuming that we're using basic Boolean index only, and we will ignore positional index, okay, for now. Okay, and let's consider the different schemes. Okay, so this I have already talked about. Why? Now let's look at the default behavior. Okay, the naive way of storing the dictionary, right? Remember, the dictionary consists of multiple entries, and each entry is the term plus the frequency of the term plus the pointer to the posting, right? So I remember early on I said that in the worst case, we're assuming that 20 bytes can hold a term. Okay, we're assuming that English word is as long as 20 bytes, right? 20 characters. So 20 bytes can hold a term, and then we need 4 bytes each to store the 2 integers, right? So that's the default behavior. So each row takes 28 bytes, right? Each row takes 20. This is a default behavior, okay? The naive way. So 28 bytes per term. If you have 400 million terms, 400,000 terms, that amounts to 11.2 megabytes. So that is our starting point, right? It takes us 11.2 megabytes to store the dictionary for our RCV dataset. Okay. Now, since we know that for English, right, a lot of English words are much shorter than 20 characters, right? That's one thing. Number two, even if you allocate 20 characters, 20 bytes for this, right, you still cannot handle long English words like this. Okay, this is much longer than 20 characters, right? Or this. Okay, So this is not the solution. Using a fixed length to store the terms is not the solution. Rather, we should use variable length storage for the terms. All right, so how should we do that? Okay, on average, we know in English, on average per word in English is 4.5 characters. Okay, but we cannot use this one as well, right? Because using this one you will not have enough space to store many long tail words, right? So how do we do that, right? So short word dominates the token count, okay, but not the type average. Remember we talked about this, right? There's 44.5 and 8, right? These two numbers, okay. This is the average character per word, and this is the average dictionary word in English. Okay, so so there's this difference between these two, because in our dictionary there are many other tokens that are not really English. Okay, so in essence this is smaller. Okay, so one key idea we have here is that instead of storing each word individually in a fixed width fixed number of bytes, we can store our dictionary as a long string of characters, all concatenated together. Okay, one after another, right? All concatenated together. And then what we need to do here is that we do not store the term itself, but rather we store a pointer to the term, to this long string of characters. Okay, so the pointer to the next word shows the end of the current word. All right, that's the smartness of this. Okay, so the pointer to the next word shows the end of the current word. Okay, so the total string length, if you do this, right, if you do this, you are not wasting any space, right? So the total string length will be roughly, of course this is again, this is a estimate. Okay, suppose that the average length of English words is 8 byte, right? So you would take 3.2 megabytes to store this long string. Okay, because we have altogether 400k unique terms, right? So in total is this. Okay, and then for each of this thing here, right, the pointer, now we know that the total length of this is 3.2 megabytes, right? So the pointer needs to resolve this, and therefore we only need to take the log of this, which is 22 bits, that is roughly equal to 3 bytes. So you only need 3 bytes here, okay, to index into this long string and find the word you want. Okay, get it? That's 3 bytes here, then this is 4 bytes, 4 bytes, right? 4 bytes, 4 bytes, 3 bytes. So together you will need just 11 bytes instead of the 20 bytes that you need earlier. Okay, so if you count this, right, you need 4 bytes for the frequency, 4 bytes for the posting, pointers to the posting, 3 bytes for this. Okay, so that will be, and then 8 bytes per term in the term string. So together, this, you sum this up, right, that's 19. So together it will be 7.6 megabytes versus the 11.2 megabytes. That's a lot of saving than before. Okay, you save like almost half, right? Okay, now a second idea, an even further optimization, is that I don't need to maintain a pointer for every word, okay, but rather I can block them together. I can group several consecutive words together in a block, okay, and then I only maintain a pointer, for example, every 4 terms. Okay, but because now you don't do this, you have to maintain a small number after each word now, and this number indicates how many characters are there. Otherwise you don't know, it's like a boundary, right? You have to bound each word. Okay, so this 9 here indicates that the next word has 9 characters. Okay, this 8 here indicates the next word has 8 characters, and so on. All right, and because the number of characters within a word cannot be more than 256, right? So you just need 1 byte to do this. Okay, you need 1 byte to do this. Okay, so yeah, that's the thing. So together you will, this one, because of the blocking, right? Assuming that the k is equal to 4, then you can save 9 bytes on the 3 pointers. You don't need pointers anymore, but then you have a pointer here. Okay, but you lose 4 bytes on the term length, because every term now you need to add 1 byte to it. So you lose 4 bytes. You save 9 bytes. Okay, so the net gain is that you use 3 bytes per pointer without blocking, which is 12 bytes, right? Now you use 7 bytes. So that's a further 5 byte saving per block. Okay, so this will shave another 0.5 megabytes. So now the total size of the dictionary is down from 7.6 megabytes to 7.1 megabytes. Okay, but of course you can save more with larger k. Okay, you can save more with larger k. All right, but of course if you have larger k, that will also mean that your search time is longer. Okay, because whatever that's inside your block, you have to search them linearly. Okay, so yeah, actually I've told you the reason already. Okay, so this one asks why we don't want to go for a larger k. Okay, but actually there are other reasons, right? So anyway, this is the dictionary search without blocking. Without blocking, every term is a node in the tree, right? So if you want to search for a particular node, assuming that you have a balanced tree, it takes only this many comparisons, right? Roughly equal to 2.6 comparisons to get to a term. Okay, so but if you have blocking, your tree becomes like this. Okay, so these are the terms that are blocked together. So inside here, this becomes a linear structure. Okay, and then you need 3 comparisons on average to search for a term. Okay, so everything is a trade-off, right? So there's pros and cons in this. Okay, now another thing, a further saving you can do is something called front coding. Okay, front coding is equivalent to what we call prefix compression. Okay, what does that mean? That means there are certain words that are similar to each other. They share the same prefix. For example, look at this one, right? Suppose in your dictionary, you have these 4 terms: automata, automate, automatic, and automation, right? So if you put them into your long string, right, where each string contains a length, right, and then you put them into the one block, right? But actually these things share the same prefix automat up to here. Okay? So why do you want to waste the space to store these things here? Right? There's no point doing that. So one thing you can do is that you can convert this string into this string. Right? So you just have a common prefix in the front with a star here to indicate that there's some remaining trailing characters. Okay? And then you just need to put your trailing characters here. And the one here indicates how many characters are there. Okay, 1 character, 2 characters, 3 characters, and so on. Okay? So this becomes to resemble general string compression. Okay? Right, so this, okay, at the end of the day, let's look at how much saving we have, right? Initially, when we use fixed width storage for the terms, we need 11.2 megabytes, right? After we convert that fixed width storage into a dictionary as string approach, we shave it down to 7.6 megabytes, right? After blocking with k equal to 2, sorry, k equal to 4, it's 7.1, and if you add from coding, it's 5.8, right? So there's a lot of savings here. All right, so that was how to compress the dictionary. How do we compress the postings? Okay, the posting file is much larger than dictionary, usually by a factor of 10, right? Because every term is associated typically with many documents, right? So on average, the number is at least 10. So the key consideration is that you want to store each posting compactly, okay? And a posting for our purpose is a document ID, which is a number, right? It's a number. So because in general we have, in this particular case, we have like 800,000 documents. So we would need log of that number of bytes, of bits, which is 32 bits per document ID, which is actually 4 bytes of integer, right? So by default, without doing anything, you need 4 byte integer to store the document ID, okay? Of course, we can also take the log of this, right, which is 20 bits per document ID, okay? So this is smaller than this, okay? This is the default. This is just to use the integer, right? So it's 4 byte integer. So if you want to be smart, use this, right, 20 bits. But our goal is to use far fewer than that, okay, in our compression. So let's see how we do that. Well, before we do that, let's think about a situation here, right? So you have a situation like a term that is really long and really weird and rare in your document set. So this word occurs maybe only one document out of a million, okay? So we would like to store this posting using the full 20 bits, okay? For other terms which are more frequent, like the, which appears in almost every document, using 20 bit per posting seems too expensive, right? Right. So we would prefer to use a 0,1 bitmap vector in this case, okay? Because this guy is too frequent. So all I need to say is that it appears or not appears at all, okay? So we will use a 1 bit map vector in this case. You get it? All right. So we store the list of documents containing a term in the increasing order of documents. So this is the conceptual case, right? Conceptually, computer appears in document ID 33, 47, 152, 159, so on, okay? So, and of course, one obvious improvement over that is that we can try to minimize the numbers, reduce the size of the numbers by storing the gaps. Okay, for example, we identify that 154 and 159, they're very close to each other, right? So why do I need to store these two large numbers? Well, I can just store the small number, right? Store the difference, which is 5 here, okay? So hopefully most gaps can be encoded or stored with far fewer than 20. Okay, so this is the first idea, to store the difference. All right, sort the document ID first, and then store the difference rather than the numbers themselves. Okay, let's take a look at this, right? So this is the, right? So look at this. Because the happens every single document. Okay, so the gap will be just 1 here. So you need just 1 bit to do this, right? But if you look at this guy is very, very rare, right? So the gap is a big number. Okay, so you see this difference, right? So that's why we want to know about the Zipf's law earlier, right? So we know this relationship. So our goal is that we want to use roughly 20 bit per gap for a very rare word, but for very frequent words, we want to use roughly 1 bit per gap. Okay, so if the average gap for a term is G, we want to use log G bit per gap entry. The key challenge is to encode every integer gap with about as few bits as possible for that integer. And this requires variable length encoding. So the next thing that we are going to discuss here is about encoding numbers. Okay, previously we were talking about encoding strings. This one is about encoding numbers. Actually, the next few techniques that I'm talking about are borrowed from information theory. Okay, so those guys have a lot of fancy algorithm and encoding methods, right? So the first kind of code that we look at is called variable byte code. All right. So we begin with 1 byte to store. So for a gap value, right? This is a gap value G. We begin with 1 byte to store G and dedicate 1 bit in it to be a continuation bit C. So if G is less than 127, binary encoding it in 7 available bits and set C equal to 1. Okay. Otherwise, encode G's lower order 7 bits and then use additional bytes to encode a higher order bits using the same algorithm. Okay, so this is like you incrementally use more bits if your G is big. All right. So at the end set the continuation bit of the last byte to 1, and for the other byte C is equal to 0. So this C here, this continuation bit indicates whether you want to go on, keep going. Right? So it's 7 bit at a time, 7 bit at a time, and the continuation bit just tells you whether you should read on to get the whole number. Right? So that's the basic idea. So let's take a look at this, right? So if you have 2 document IDs, 824, 829, and then this, right? So this particular term appears in these 3 different document IDs. So the gap is 5 and 214,000 plus. Okay, so if you look at the VB code of this, right? So for this 5, it will be like this. For this guy, which is a larger number, it will be like this. Okay, that's the thing. For this, there's no gap, so it will encode this thing directly. Okay, so that will be the thing. So basically, it's a pay-as-you-go approach. If you have larger numbers, the code is longer. Okay? If a small number, the code is smaller. Alright? So this is binary. By the way, this is binary, right? This is a binary number. Okay? So the posting will then be stored as a byte concatenation, which is this thing. Okay? So the last bit of each thing is like, it tells you where to stop. It tells you the delimiter, right? Like here, you stop right here. Right, and then you stop like here, so here, and so on. Okay, so you need a way to tell you where to stop, basically. Okay, so the key property is that VB encoded postings are uniquely prefix decodable. By prefix decodable, that means I can just look from the front, and I know where to stop. Okay. For a small gap, notice here, for a small gap here, VB uses a whole byte, which is still not good enough. Okay, so there are other variable unit code, right? Instead of bytes, we can also use different unit of alignments, right? Like we can use this, and even 4 bits. Okay, variable byte alignment with space, we have many small gaps, right? So in the case of many small gaps, you will use the nibble 4 bits instead of using the whole byte. Okay, so there are some recent works on word align code that pack a variable number of gaps into 1 word. Okay, but we're not going into that. Okay, unary code. Unary code basically means that you represent n as n ones with a final 0. This is okay, so basically if you have 3, right, you will represent 3 as 3 ones and then 1 0. Okay, this is a way of converting. This is a very simple way of converting an integer into binary numbers. Okay, so for example, unary code for 40 will be 40 ones followed by 1 0. Unary code for 80 will be 80 ones followed by 1 0. But this doesn't look very promising, right? Because for even a small number like this, you end up with very long strings of binaries. However, we can improve that by using something called gamma code. Okay, so you can compress better with bit level codes. Okay, gamma code is one of such bit level code. So you represent the gap G as a pair of length and offset. So the offset is G in binary with the leading bits cut off. For example, if it's 13, right? 13 is the binary. Its binary of this is this, right? So you just cut off the first bit. It becomes 101. And the length is the length of the offset. So if it's 13, the offset is 101. This is 3. Okay, the length is 3. It's the length of this offset. Okay, so we encode the length with unary code. This is where you use the unary code in the previous slide. Okay, because this length is not large, so this thing will not be too large. Okay, using the unary code on arbitrary integer will be a disaster, but using it on a length of the offset, that's okay. Okay, that's again the genius of this. So gamma code of 13 is concatenation of the length and offset, which is this, and this is okay. This is only 7-bit, okay, for 13. All right, so if you take a look at examples, right? So these are the original numbers, right? This is the length, this is the offset, and the concatenation of that becomes the gamma code. Okay, this is the gamma code. So the property of gamma code is that if you have a gap G, okay, you can encode it using basically 2 times log G bits. Okay, the reason is that the length of the offset is log G, and the length of the length is log G plus 1. Okay, so together is 2 log G plus 1. All gamma codes have odd number of bits, and within a factor of 2 possible, best possible, log 2G. Okay, and again, gamma code is prefix decodable. All right, and it can be used for any distribution and parameter free. All right. However, in practice, okay, machines have word boundaries such as 8, 16, 32, 64, and so on. Operations that cross the word boundaries are slower. But remember, in gamma code, you may have like arbitrary number of bits, right? So when you do operation, you may cross the boundary of the words, and that can be slow. Okay, so as such, we would need to align the variable byte encoding and make it more efficient. Okay, but regardless of this efficiency, variable byte is conceptually simpler at a little bit additional cost in space. All right, so if you look at this, right, this is the summary of what we have done so far, right? Our starting point is 11.2 megabytes, which is the default, right? So after we have done the everything with the dictionary terms, right, we end up with this number. This is after we've compressed the dictionary, all right? And then given that the collection, right, markup and everything, this is the size of the total collection. If you remove the markup, XML, HTML, whatever, you end up with this many bytes, right? So the matrix, the document term incident matrix is 40,000 megabytes. And after compressing, if you uncompress, if you don't compress the posting, right, the posting will be 400 megabytes, all right? And if you compress it using 20-bit, that's 250 megabytes. If you do variable byte encoding, it's 116. If you do gamma encoding, it's 101. So in the end, it's these two things summed together. Okay, dictionary plus posting. Okay, So in summary, we can now create index for highly efficient Boolean retrieval that is very space efficient. Okay, only 4% of the total size of the collection is needed, and only 10 to 15% of the total size of the text in the collection is needed in the storage. Okay. However, we have ignored the positioning information. Okay. So space savings are less for index used in practice, but techniques substantially the same. So in practice, so I've told you thought of a theoretical approach, right, in which we see a lot of savings. In practice, is not as much savings, but generally speaking, the approach is similar. Okay, so for today's lecture, you should look at some of these chapters, okay, in the textbook.